Okay, good morning, everyone. Are there any questions about yesterday? Okay, well, you can ask me questions later as well. So today I want to, so these are the last lectures. So it's going to be about complex actions in the complex plane. And this is something I started with at the very end yesterday. Namely, we take the sign problem or the complexity series, and so we extend our configuration space to become complex. So at a configuration space, or the field space, to become complex. And as we will see, this avoids the sign problem in some cases completely, and it also gives a new way to think about the sign problem and other approaches. So there's three kind of approaches on the market that look at this. So the first one is complex Langevin dynamics. And then we have Lefschetz-Timbos. And then we have something called anti-holomorphic flow. And all three of these explore the complex plane in a slightly different way, and they can all solve the sign problem in this, the cases where you can work it through completely. But it should be said that these are all still kind of speculative in a way, or in progress. And only the first one, complex Langevin dynamics, has been really applied to QCD. But not at zero temperature, but only, say, at a relatively high temperature. So maybe in the quark-gluon plasma, say. And also there, it's not yet, it's not yet a completely a method which has been completely settled into a workhorse to compute things. So in other words, there's a lot of scope to work on this and see what possibilities there are. So what I'm going to do today is just give you the kind of the basic ideas, so you can understand the literature and maybe contribute to these questions as well. Okay, so to do the basic ideas, we're going to simply consider some simple integrals. So most integrals are considered just zero-dimensional integrals. So z is the integral over x e to the minus sx, like this. So these are really simple integrals, obviously. And I'll consider a few examples. For instance, s is a half a x squared plus I bx. Which is a Gaussian, well, I will only consider Gaussian integrals actually, or a half a plus ib times x squared. So these are Gaussian integrals with, they both have complex actions in a slightly different way, but the advantage is that we can just compute everything through using any of these approaches analytically. And so we get an understanding of how they work. So if I take the first one, if I just evaluate the path integral, so it's just a Gaussian integral, so it's 2 pi over a e to the minus a half b squared over A, so it doesn't really matter what it is. But I'm telling you this because we can play all the same games that we played before. We can compute the phase-quenched path integral, which simply means putting B to 0 here. And if you do that, you can compute this reweighting factor, so the ratio of the phase-quenched, well, I have to do it the other way around. The ratio of the full theory over the phase-quenched theory, e to the I phi, say, where e to the I phi is now just e to the I bx. It's the complex phase of the action, of the weight. And so that's just z divided by z at 0b. And that's just e to the minus a half b squared over a. So I'm showing you this to basically argue we can just do all the same tricks that we do in field theory. We can define phase-quenched path integral or partition function, look at the average phase factor. So, you know, we can just pretend it's field theory, even though it's not, obviously. And so one thing you notice, this is not field theory, that there is no exponential volume factor here, no suppression with volume. But that's, of course, because we have a simple integral, so there is no volume factor. So if I would want to make this a little bit more realistic, I could just put this whole partition function to the power n, which would put a kind of a volume factor in the exponential. So I can even make it more realistic, but I won't do that. Okay, so we'll pretend these actions are like field theories. They have, we can compute phase-quenched partition function. They have an overlap problem, etc. And so I want to solve these equations now, these path integrals, functions, without important sampling. Because if I do important sampling, I run into this problem of having a complex weight or having an overlap problem. So I want to avoid important sampling. And so what I started with yesterday is to say, let's take inspiration from Brownian motion. If you consider a particle in a heat bath, this particle will get into equilibrium with the heat bath and will take the temperature of the surrounding particles if you wait, long enough. And so in other words, the properties of this particle, of the Brownian particle, can be deduced by just solving a Langevin equation which describes this trajectory. So in other words, the system equilibrates and takes on the properties of the heat bath without actually having to do important sampling, so to speak. So this sounds a little bit vague, but let's simply do this. So let's write down the Langevin equation. So what is the goal? Let me first write down the goal, and then we can see whether we achieve it or not. So the goal is to compute expectation values. And since we are in a simple theory, these expectation values are basically moments of x. And since it's a Gaussian theory, there is actually only one that we can compute that is independent. So it's only the second moment that we need to compute. And so we want to compute the second moment, essentially, so without using important sampling. So I want to devise a scheme that I can solve numerically, compute moments or expectation values. There's a C missing here. Without important sampling, is something which can be numerically implemented. Of course, I know the answer. The answer is 1 over A. Okay, so now I'm going, mixing up two things. So we know the answer because it's Gaussian. So what is the answer? Well, I can get the second moment x squared if I differentiate the action of the partition function with respect to a. Because if I differentiate this expression with respect to a, that brings me an x squared down. So in other words, the moment we want to compute is x squared is minus d log z dA. And that's a factor of 2 here because there's a half in the action. If I take this derivative with respect to a of the log of the partition function, I get exactly the moment x squared. And I've computed the partition function here, so I can take this derivative, and if you work it out, you get a minus b squared over a squared. Yeah, so this you can do in your head or on paper. I'm just using all the tools that we know of statistical physics or field theory. I have a partition function with two external parameters, a and b. I want to compute moments of the field, which is just x in this case, and I can do it by differentiating with respect to a or, with respect to b if I wanted to. And if I do that, I get the second moment x squared in terms of these parameters. And so the goal is now to compute the same expectation value, not using the analytical result, but by solving some equation which can also be solved numerically, and which does not rely on importance sampling because there's a complex weight problem. Yeah. So let's try to do that. And so this is done by writing down a Langevin equation. So the Langevin equation is an equation for, say, the degree of freedom, x, which depends on time now, which is the Langevin time. And there is some drift term here, which I'll call k of x. And there is a noise term here. So this is the time derivative. This is the drift term. And this is the noise. And the drift term actually follows from the action. And so it's equal to minus ds dx. And I'll show in a minute why that is the right drift term. And so if this particle is moving around, it's getting kicked around by the noise, but its dynamics is governed by this force, essentially, and so we see what happens at late times. So the noise is taken to be simple Gaussian noise, not correlated in time. So it will be of this Gaussian noise, and we'll determine later why the weight of the noise, or the strength of the noise is as it is here. Now let's try to do this, and let's start with a simple case where b is equal to 0. So the action is simply real, I have a x squared. In this case, everything is real, so it's even easier. So the equation, the Langevin equation, is x dot is minus ds dx plus eta. So this is minus a times x plus eta. This is a stochastic differential equation. So there's a deterministic part and there's a noisy part. And if I solve it simply by integration, I have to integrate over the noise here. So I can write down the solution as xt is x0 e to the minus a t. Check it. And then there's an integral over the history of the noise. So I have to integrate over all the kicks that this particle has received in the past, e to the minus a t minus s. So this is a solution to a stochastic differential equation. So this is anyhow an interesting topic because for theoretical physics this is something you should know, but maybe you don't encounter actually in undergraduate courses. We can check that this satisfies this equation. If I differentiate with respect to t, I get a minus a down here and also a minus a down here. So I get minus a times the solution. So that gives you the first term. And if I differentiate this upper boundary here, I get eta of t times 1 if s is equal to t. So that gives the noise here. So it indeed satisfies the equation of motion. So that's good. And then we know that a is, so I take a to be positive. Otherwise the Gaussian integral wouldn't converge. And so this is the initial condition is x 0. So this term goes to 0 exponentially. So this dependence drops out. The dependence on the initial condition where I started trajectory drops out as t goes to infinity. So all I'm left with is this summation over of the integral over the noise. So to determine the trajectory. The noise is Gaussian, as we said here. So if I just take the expectation value of x, I would just have the expectation value of the noise of a single power of the noise, which is 0 because it's a symmetric, it's a Gaussian noise. So x expectation value is 0, as it should be because the action is even. So let's look at the second moment. So x of t will go to 0, which is the correct answer. So let's now look at the second moment. X squared of t. I did it for the same, yeah. So we can ignore the initial condition here because this is exponentially damped. So we don't have to write this down. So let's only look at the noise term. So 0 to t ds. Another integral 0 to t ds prime. Then I have these noises, eta of s prime. And then I have two of these exponents, e to the minus e a t minus s prime. And I'm taking the expectation value. So I'm putting brackets around here. Say again? 2t, yeah, exactly. In my head, I was thinking, how does this 2 get absorbed in the exponent? But it's indeed, this I had, but this not yet. 2t, thank you. So this is for any time. This is the Gaussian noise here, where the expectation value is non-zero now. So this is 2 delta s minus s prime. So I can do one of the integrals over s prime, say. So I end up with 2 times the integral from 0 to t over s. And then I have here e to the minus a 2t minus 2s. And so now I can do the integral e to the minus a 2t minus s 1 over a. The 2 cancels indeed. I'm integrating over s, so the sign is correct between 0 and t. And so I'm doing it for s. So if I fill in t, I get 1 over a. So in the limit now that t goes to infinity, this is 1 over a. So the lower boundary here is exponentially damped, and the upper boundary gives 1 over a. And that's the correct answer. Huh? So that's what we, up there, we computed x squared just from differentiating the partition function. We're looking at b equals 0. So the second moment should be 1 over a, and it is indeed 1 over a. But we solved it. We solved the path integral now, essentially, by looking at the trajectory, an average over trajectories of this degree of freedom, solving it, letting the system come to thermal equilibrium, and at late times then get the right expectation value. So that's the idea here. Now this one is a little bit, well, first, is there any questions about this? This was all real, so this is should work in any case. And so let's make it a bit more interesting now, and let's take B non-zero, so in the complex case. So B non-zero. So now we have, so I'm going to basically now write Z to be X plus IY. So I go into the complex plane now because the drift is complex. What is the drift? K is minus ds dz is minus a z minus I b. It's up there, the integral, huh? A half az squared plus ibz. And so the Langevin equation would now be z z is minus dz ds plus eta. And because the drift is complex, it has this IB here. I made the degree of freedom complex, and so I can write this now as two equations for x and y. So I get two real equations for x dot and y dot. For here I get the real part, so it's minus ax plus, and here I get the imaginary part minus a y minus b. So I get these two coupled equations now for the real and imaginary part of the coordinate. And what I've chosen is to only have noise in the real direction. I'll come back to this in a minute. So here we've chosen, this is a choice, only noise for the real part of the degree of freedom, not for the imaginary part. And I'll explain this in a minute, why this is a good thing to do. Now, this equation is very similar to the ones we saw here. In fact, it's exactly the same. This one is exactly the same. And this one, since it has no noise, is just the deterministic equation, so it's not even a stochastic differential equation. So again, I can just solve it. So x of t is same as before. And for y, I can just, it's an ordinary differential equation, so I can just solve it as y0 plus b over a e to the minus at minus b over a. So you can just check that this satisfies the equation. It's just an ordinary differential equation. And so we find the same answers as before. So let's look at the expectation values as t goes to infinity. But the one for x is exactly the same. So x squared goes to 1 over a. The one for y is actually just deterministic. So this is just y squared goes to this minus b over a squared, because this is y, so y squared goes to plus b squared over a. And then in principle, we also have to compute the mixed moment, x, y. But here the same happens as here. X is linear in the noise, so if I take the expectation value, it vanishes. So this gives 0. So I can solve this. So what do I do with this now? What is the point of making this calculation? What do I want to compute? Z squared, exactly. So I'm not really interested in these little components here. I'm really interested in the second moment, which is Z squared now, because I went into the complex plane. So that's x plus I y squared. And so that would be x squared. The mixed term cancels, minus y squared. And if I fill that in, I get 1 over a minus b squared over a squared. And that's, of course, a minus b squared over a squared. And that is indeed exactly the correct answer, which we got in the first place by just looking at the Gaussian integral. So we achieved the correct answer. But we've done it by integrating the equation with noise and by allowing the degree of freedom to become complex. So that's the special feature. In fact, this is something that we discussed yesterday at the very end. We've completed the square here in quite a tedious way. It's probably the most tedious way to complete a square. But we've done exactly that. We've exactly completed the square. So if this is x, and this is for the case b equals 0, we have this Gaussian integral, e to the minus a half a x squared, which is real. Now when b is non-zero, if I stay on the real axis and I plot it, I have this oscillating integral. This is for b not equal to 0. And what we said yesterday is, well, we have to complete a square, and this will be a shift in the complex plane. X goes to x minus I b or something like that. You can read off what it is there. Minus b over a is completes the square if you do this change of variables. So in other words, in the if this is x, we now shift in the y direction, and so rather than being at 0, we've shifted it in the complex plane over in a distance b over a, where the weight is real again, and that's exactly what we've achieved, because this is what you can see from the equation for y, is that we shifted the y coordinate by an amount b over a. So this is the shift in the complex plane. So in other words, we have completed the square in a quite non-straightforward manner. Now, this is a very simple example. It's Gaussian. You can compute everything. So what are we really doing? So the best way to think about this is to think in terms of probability distributions. So a Langevin process, or any stochastic process, is linked with a Fokker-Planck equation that describes how the distribution evolves in time. So let me explain that a bit. And so what we're really trying to do is to construct a probability distribution in the complex plane which satisfies the Fokker-Planck equation that underlies the Langevin process. So if we have some microscopic process, say x dot is k of x plus eta, where k of x is minus s prime, then you can show that there is an equation for the distribution, and this is called the Fokker-Planck equation. For rho of x and t. And this Fokker-Planck equation satisfies, so this will be a distribution. And this Fokker-Planck equation will satisfy the equation dt of rho of x and t is dx minus s prime of x times rho of x and t. Should be a plus there, I think. Huh? Yeah. Should be a plus there. And this is the derivation, or the link between the Langevin equation and the Fokker-Planck equation is done as an exercise. So see exercises in the lecture notes. So you can derive how these are linked. So as I'm solving the Langevin equation for this degree of freedom, and I'm solving it many times, so I take a whole ensemble of solutions, starting with different initial conditions and having different realizations of the noise, I'm actually solving an equation for this probability distribution, starting with some initial condition, starting at some initial condition at time equals 0. Now, as we saw here in this explicit solution, I'm not really interested in the intermediate behavior, because as time goes on, this will be exponentially damped and will disappear from the solution. I'm really interested only in the late time behavior. And in the same way, I'm interested in the solution of this distribution function at late times. So we are interested in rho of x and t as t goes to infinity. So what can you say about so does anybody see a solution to this equation that satisfies I see some people nodding. What solution for rho satisfies the equation? Simple one that you can see immediately. Okay, the person who was nodding, what is the solution?
So that e to the power of minus s prime x comes.
Exactly, something like that. E to the minus s actually satisfies this equation, because if I then take the derivative of this, it will bring down a minus s prime. So that's exactly right. So we find a stationary solution. Rho of x is e to the minus s of x. Because I can just look at the second part of the equation here. If I take the x derivative of the exponential, I get minus s prime times the exponential, so it cancels this. Yeah.
So the exact form of this Fokker-Planck, I mean, if you start with Langevin, it depends on whether you choose e-tor or e-tor.
Yeah, so indeed, yeah. So I won't go into detail there, yeah. So I've derived in the exercises, there's a lot of e's here, but it's the right number of e's. In the exercises, I actually derive it by using a discretized equation. And I think it's Ito calculus, but yeah. So the fact that we, well, at least for the real case, that we found the correct answer, so x squared was 1 over a, is not a surprise, because we're actually solving the distribution as a whole, and we see that there is a stationary solution, which is the one we want, e to the minus x. So that's why a Langevin dynamics description works. Of course, what I haven't said, I mean, this is only the stationary solution, but what is quite beautiful, actually, is that you can prove that this solution is reached exponentially fast. if the action is real. So not only do you get the right distribution, you actually can reach it exponentially fast if the action is real. So I won't do that here, but this is something you can show. So that basically shows that for real actions, all of this is fine and under control. Now, what happens now with complex actions? Because that's what we're really interested in. And here is where the difficulty obviously emerges, because if exactly the same would happen for complex actions, then we would be done, because we would just take this complex Langevin equation and we would have solved the sign problem. So, but we haven't, so that already tells you that something is going on. So now let's go to complex Langevin and see how this works. So let me make sure I put all the signs in. So I'm going to consider these coupled. I'm going to consider this equation z dot is k of z plus eta. So the same equation. K of z is minus s prime. And we take the case that S is complex. And so to solve this, say, on a computer numerically, if Z is complex, I would have to write it in terms of two real numbers. So I'm going to write the equations for X and Y. And so I get these two equations. X dot is K, I call it Kx here, plus beta x. This is Ky plus beta y. So I have, in this case now, complex noise. Kx is minus the real part of S prime. Ky is minus the imaginary part of S prime. And I'm having so essentially this noise here is the combination of an x plus I and y. So the original noise is made out of these two. And so I'm going to call the strength of the noise, that's what I was really wanting to write down. So what is the strength of the noise? Eta x t eta x t prime is 2, and I'm having a normalization here, delta t minus t prime, and the same for y. So it's again Gaussian noise with strength 2, but now I have an unknown factor lambda, and because my normal noise eta t in the original equation is normalized to be 2, it just means that lambda x minus lambda y should be 1. So that's just the normalization from the fact that in the original Langevin equation I had an eta with strength 2. So if I write it in real and imaginary components, it turns out I have a freedom in how I normalize the noise of just the real component to the imaginary component, but if I combine it, it should have the right strength. Now, what can we say about this equation, this set of equations now? Actually, it looks very similar to the equations on the right-hand side. Here I have 1 degree of freedom, x dot is k plus the noise. Here I have 2 degrees of freedom. X dot is k plus the noise. Y dot is k plus the noise. So it's exactly similar. And so I can write down a Fokker-Planck equation now for the distribution, which now not only depends on x, but will be a distribution that depends on x and y. And so the distribution depending on x and y and t. And just looking at this equation, actually, you can write down this Fokker-Planck equation. A straightforward way. And so the equation for P, the Fokker-Planck equation, for this combined Langevin process is dt P of x, y, and t is dx lambda x dx minus kx plus dy lambda y dy minus ky on P, x, y, and t. So it's essentially a doubling of the original equation for only x. Here we only had x, so we have these x derivatives and s prime or k. And here we have x and y, so the equation is essentially twice as long. The only kind of interesting thing is that the noise enters here, but if you would keep the noise of arbitrary strength in this original one, actually there would also be a factor there. So that's what's done in the exercises. So they take exactly the same form. And again, this is a probability distribution. So this is a completely real equation. So k, the drift is real because I took the real and imaginary part. So so this should be real and positive. And so if I solve this Fokker-Planck, if I solve this Langevin equation, this complex Langevin equation, I'm effectively sampling or solving the distribution P of x, y, and t. Now that's all great. And for this equation here, we've then immediately could see the stationary solution as e to the minus s, which is great, and you can even prove it's reached exponentially fast. Now it turns out that this equation, although it looks very much the same, cannot be solved. I mean, it has no generic solutions, has no stationary solutions. In fact, you cannot even prove that a solution exists. So there are complex Langevin processes which are unstable, and so there is not even a stationary solution or a bounded solution. And that's where the problem is. This idea of going into the complex plane is very straightforward to write down, but there's no general solution to this equation. So no general solutions for P of x, y, and t exist. And even worse, you cannot prove existence or convergence. So in other words, if we, when we solve this complex Langevin equation, we're essentially completely in the dark because we do not actually know what kind of probability solution we are creating here. So how can we go about this? Because when we do this, when we solve this equation, it turns out that you can just do it on a computer and it gives you a result. It does converge. It does give you something. So we have to find another way of analyzing this equation, not by finding a general stationary solution, but some other approach to support the numerical findings. I should say, so I'm making it look very bleak here, obviously, but we have applied this procedure to four-dimensional field theories with silver blaze problems and phase transitions, and also to QCD, and then it does work. You know, for some theories, it completely solves the sign problem, and for QCD, it works at high temperature. So there's a big motivation to make it, to extend this proof here. So let me just add that here. So there is there's significant numerical evidence that complex Langevin works in relevant theories. So, for instance, this phi to the fourth theory with chemical potential, SU3 spin models with non-zero chemical potential, and also, say, QCD at high temperature. So, so there is a real motivation to solve this because there is, this is all based on numerical evidence that it works and it converges and it gives a good result. So how can we go about this? So we want to essentially find some properties of this distribution P of x and y, which somehow related to the original problem, which was e to the minus s. We originally want to look at that. So how can we go about that? Well, for this we have to combine these two Fokker-Planck equations we have. So we had this one, s is minus ds dz plus eta, where s is complex. For this one, we have a Fokker-Planck equation, rho dot is the one which is there, dz dz plus s prime times rho. And this one has a stationary solution, rho is e to the minus s of z. But if the action is complex now, this will be the complex weight. So up there I discussed it for a real action, and it gives the proper probability distribution e to the minus s of x, but it can give the same reasoning for a complex action, and I can say, okay, there's a formal solution to this equation, e to the minus s of z. However, this is not a probability distribution because this is complex valued. Instead, I have to look at this equation for x and y, and this will give me this equation for p of x and y. And this is the equation I wrote down here. And this one here, p, is real and non-negative if it exists. So I would like to achieve this with some complex function, complex weight. I'm solving this process here with a real and positive weight, and I want to link those two. That's the idea. Now, how are they linked? Basically, via the fact that I want to get the same expectation values. So I want to compute, say, O, an observable, the expectation value of an observable, and this can be defined either. So what I want to get is the integral with respect to the complex weight, like this. If this is e to the minus s, then this is exactly what I want. But instead, I'm computing something else. I want to compute, solve the Langevin process. So what I'm solving on the computer is the right-hand side. It's the expectation value of an observable as a function of x plus iy with respect to this real and positive weight p, which I do not know what it is. So this is what we want, and this is what we do. And so we want to link these two observables, so these two expectation values, to make sure that we are computing the right one. So that's the way to do this. Now, a lot of work has gone into this. So you can establish this by using Cauchy-Riemann equations. And so you can then establish that this holds by this I mean that if you solve the Langevin process for this Fokker-Planck distribution, you do get this expectation value. So you can establish this holds provided this distribution goes to 0 essentially exponentially fast at large y. It's very roughly what the statement is. Why is it? Well, you have to, if you use the Cauchy-Riemann equations, you do partial integration. If you do partial integration, you pick up boundary terms, and the boundary terms do not contribute if the distribution drops very fast. So that's kind of the way to look at this. So in the complex plane, where this Langevin process takes place, you want to make sure that the distribution is sufficiently localized. So before coffee, let me do one more example where this all is still analytical. It's still an analytical example, but you can see exactly how it works. Still a simple integral. So again, I'm taking a Gaussian integral, but this time I make it complex by putting the making the weight, the prefactor complex, like this. This is also an exercise in the lecture notes. So obviously on the real axis this is oscillating. We can write down the Langevin equations for this. So z dot is minus a plus I b times z. So I can split it. I can write z is x plus I y, and so I get two coupled equations for x and y. And these are now properly coupled because there is a x and y are mixing here, as you can see, because this is complex and this is complex. So you get proper coupled equations. But since it's Gaussian, we can kind of guess that P of x and y is Gaussian too, because that's the beauty of Gaussians, that once something is Gaussian, everything is Gaussian. And so we can actually solve the Fokker-Planck equation for this example explicitly, and it turns out it's the exponential of minus some coefficient alpha x squared minus beta xy minus gamma y squared, where these alpha, beta, and gamma depend on A and B. So if we solve this Langevin process for x and y, and we wait long enough, we're actually sampling from a Gaussian distribution in the complex plane now. And so this P of x and y in the complex plane, x and y, well, it's a Gaussian, as you can see, with width in all directions, is actually some kind of properly Gaussian distribution in the two-dimensional plane. So this is when B is non-zero, and when B is 0, of course, it's all on the real axis. And so as I turn on B, this Gaussian is spreading out in the complex plane, and I'm sampling from this two-dimensional distribution by solving the Langevin equation. And then the final remark before coffee is that I can link the original distribution. So let's call this, so I can link the original distribution and this two-dimensional distribution in the complex plane by using this relation there. So let me see how I wrote it. Yeah, so I want to I'm really interested in this type of observable. So observable which depends on x, and rho of x is the e to the minus s of x. But as we said, instead we are integrating dx, dy, p of xy, o of x iy. The right-hand side is what you actually do. But in this case, we've determined this p of x and y is this Gaussian. And so since it's analytic, I can manipulate these expressions a little bit. And so I can, for instance, shift the x variable by an amount iy. So I'm allowed to do that. So I can write this as dx o of x dy p of x minus iy y. So I'm doing here, since everything is analytic, I'm free to change variables and shift things around. So I'm redefining x by shifting it by an amount iy. So it disappears from this, from the observable. It only appears here in this distribution function. And since we know the explicit expression, you can indeed check that this is equal to rho of x, the original complex weight. And so this is another way to get complete agreement between the two approaches. So this is a check, basically. So this gives me the original weight back on the real axis with the observable. So these are kind of the games you play with complex Langevin dynamics. You have a complex distribution on the real axis, but a real distribution in the complex plane, and you try to evade a sign problem by going into the complex plane and solving that process there. Okay, any questions? Yeah.
So, if our aim is to generate something whose solution is the exponential of this minus s, then why do we have to use this Langevin equation? We could define another one.
Yeah, so that's a good point. So we could, based on this, this basically we want to, this is what we want. This is what we get very generically because we go into the complex plane. So in a way what you say is our task is to find a distribution which is proper distribution, so real and positive, which if I carry out these integrals, I get the original one back. That's exactly right. Now, but it turns out this is a really hard question, actually. So, in fact, there's some theorems. I forgot now exactly what they say, but something like, maybe there's a theorem that it exists, or something like that. So, so it is, I forgot now, actually. So, but there's papers by, a very old paper by Weingarten, and more recent papers by Salcedo, about the existence of this relation and properties of this distribution then, yeah. So indeed, so Langevin dynamics is one way to achieve this in a very constructive way, namely by solving a microscopic equation and essentially constructing this distribution by collecting a lot of data on the computer. So it's a very pedestrian way to do it. If we could do this in more general ways for the whole distribution, then the problem would be solved, because then we could just say, use Monte Carlo simulations on this real and positive weight. So that would be the ultimate dream, that you find a probability distribution which is real and positive, which satisfies this relation, because then you just do Monte Carlo on this. And that's done, problem solved. Yeah, good question. Yeah. Other questions? Okay, so let's have some coffee. Okay, so in this last lecture, I want to talk about the two final approaches to go into the complex plane. So that's the left-shade symbol first. So we've seen that it's useful to go into the complex plane because the weight is complex. And so this is another approach to do which has relations with Langevin dynamics. I mean, there's some things which are similar and some things which are different, so it's quite interesting. So what was the idea? So again, I'm going to consider a simple integral like this with a complex action. And what we saw in the Gaussian case was, of course, that you complete a square. So what is the generalization of completing the square? Is basically to do a steepest descent. Find a saddle point and do a steepest descent calculation. Say, so find saddle point and do a steepest descent. Now, typically, if the action is complex, the saddle point will be somewhere in the complex plane, so that naturally takes you there. And then the steepest descent will be some kind of contour around the saddle point that tells you how to do this. Now, this has a very interesting mathematical, really rigorous mathematical basis. Which is linked to something called Moore's theory. And it was, it's basically been used to extend the definition of the integral into the complex space again. And it was kind of revived by Witten in 2010, and then a few years after that picked up by people doing lattice QCD to see if this method can be used for the sign problem. So what is the idea here? Is that you it's basically you find all saddle points so let me call them ZK, so that the derivative of the action is 0, so stationary points. So maybe we should call it stationary points, or actually it's called critical points in the language of Witten. So critical points are those where the action has a extremum, and then deform the integration contour to what are then called thimbles, which are basically the path of steepest descent. And because the saddle point or the critical point may lie in the complex plane, and you're deforming your integration path, you typically end up in the complex plane. So let me give a very simple example here, just to get the mind started. So again, I'm going to use a low-dimensional, zero-dimensional example. Zs is a half sigma z squared plus lambda z to the 4. And again, this kind of math parameter is complex like this. So if this is complex on the real axis, the integral is highly oscillating, but I'm now going into the complex plane. So what I have to do is first find the critical points. So what is the derivative is sigma z plus, okay, I put a 1 over 4 here, plus lambda z cube. So that's z sigma plus lambda z squared is 0. And so there's 3 critical points here. One is in the lies in the real axis, so let's call that z0, just the origin. And then the other 2, z plus and minus, lie in the complex plane. Well, I can just read off what it is says. So it's minus sigma over lambda minus sigma over lambda and then the square root, so like this. Yeah. So if sigma is complex, well, anyhow it's complex, but if sigma is complex, these two lie in the complex plane. So if I draw these saddle points, there's one at the origin, there's one here, and there's one here. So these are what's called the critical points, or the stationary points, where the action is minimal. And so then it turns out I can now determine the path of steepest descent and steepest ascent going through these saddle points. And let me just draw them first. And they are essentially it's a deformation of the integration contour. So the one I'm really interested in is this one. And then there's one which is, so this would be the path of steepest descent. And then there is one which is essentially orthogonal to this, which is the path of steepest ascent, like this. And then there are 2 more of these paths which connect up with these ones, and goes up to plus infinity there, and this one matches up with this one, and the same on this side here. This one goes here, and the other one joins with this one and goes here. So there are 6 lines in this graph. So there are 3 paths of steepest descent, and there are also 3 paths of steepest ascent, because there's 3 critical points. Now, the one I'm most interested in is the one I drew in bold, because this is simply a deformation of the original configuration space, the horizontal line. And so it turns out that if you integrate along this path in the complex space, you have reduced the sign problem. So what do I mean by this? It's the following. So these are the, these here are what are called, these are what's called stable, and these are unstable symbols. So these contours here, or these lines, are stable, unstable symbols. Does everybody know what a symbol is? I didn't before 2010. So a symbol is the thing you put on your finger when you do needlework, so to protect your finger. So here is just a line, but if I'm in higher dimensions, I have a critical point here. So the saddle, there's a surface coming out, higher dimension surface coming out, which looks like the symbol you put on your finger. So that's where the name comes from. So it's a deformation of the integration of the original configuration space into some curved surface here. And so as it turns out is that along the symbol, something special happens, namely the imaginary part of the action is constant. which you can prove. One way is to define the symbol to be the surface where the imaginary part of the action is the same as at the critical point, or you can prove it from the way it's defined. So in other words, it's equal to the imaginary part of the action at the corresponding critical point. Now that's really nice if we think about the sign problem, because if we then deform the integral to be along this symbol, we suddenly find that the imaginary part of the weight is no longer oscillating, it's just a constant. So that's kind of nice. So hence, I start with the path integral on the real line, say, e to z. I can now deform it and go integrate along the symbol. So I call this stable symbol J, dz, and I here have minus the real part of the action minus I, the imaginary part of the action. But this is constant. And so I can write this just as the imaginary part of the action at the critical point. And then I just have an integral over the symbol left where the weight is positive. And so it looks like we've solved the sign problem, because we're left with an integral over a real weight here by deforming the contour. Now, again, if this would be the case, we would be really happy. So there's two obstacles to this. Okay, let's see if you can guess which two obstacles you can see. Yeah, that's one. It's not one of the two I had in mind, so I should. There are n obstacles, yeah. So symbols are hard to find. Think about this plot. So here there was only one critical point that I said is important, but not necessarily. There are more critical points. So there may be more critical points. In fact, one should sum over all critical points. And the weights, the imaginary part along all of these may not be the same. So I have to combine contributions from different critical points or different symbols, which have all different imaginary weights here. So that's the sign problem that's still there. So I'll write it in a minute properly. And then there's another one which I have in mind. So I'm changing the contour here. And so if I do that, I have a Jacobian, essentially, by going into kind of in a curved manifold. And Jacobian will also be complex valued when I do this. So this, there's essentially a Jacobian symbol, because I'm no longer integrating along the straight line, and this will also be complex valued. So that's another way the sign problem reappears. So this is, in other words, this is too naive. If I want to do this correctly, I have to sum over all symbols, stable symbols. And so I can write the partition function instead. as a sum over all these critical points, e to the minus I imaginary part, which for each symbol is a constant, but it may be different for each symbol. And then there's an integral along symbol k, like this. And this integral here has a Jacobian, which I can write as some, in terms of some parameterization with the Jacobian. And in this simple zero-dimensional case, this would just be x prime plus I y prime. So in other words, it's dz ds. So I'm summing over all the stable Timbals J. Which contributions do I take into account? Well, so here I had 3 stable Timbals. I only took the bold one into account. And so this number here is an integer, which is actually what's called an intersection number. And it's basically plus 1, minus 1, or 0, depending on whether the symbol crosses the original manifold. So it's the crossings of J with the original manifold. So in the example up there, only the fat line goes through the real axis. So that one is intersection number 1, whereas the symbols going through the other 2 critical points do not go through the real axis, so they don't contribute. So that's this intersection number. So that tells you which symbols to include. And then we have these now 2 remaining sign problems. Namely, if I have more than 1 symbol contributing, I have to add up their contributions. They will all have a different phase. So how do I combine this efficiently, taking all these phases into account? So this is sometimes called then the global sign problem. Which is actually a hard one. And the second sign problem, even if I have only 1 symbol, is that I have to include this Jacobian because I'm changing my manifold. And so this one is called, so this is a complex number as well, which I have to include under the integral. And this is called the residual sign problem. And generally, this is actually quite mild, surprisingly. It's not very strong. So if you would be able to restrict yourself to only 1 symbol, then there is a lot of hope, actually, because this residual sign problem is just quite mild. So one question is 1 or more symbols. And here you could argue that maybe 1 symbol is enough because for each symbol we have essentially this partial, let's say, partition function along each symbol, And if we think about, statistical physics, then we can write it as a free energy. And it could well be that there is one symbol which simply has the lowest free energy. So this is a conjecture. Say only the symbol with the lowest free energy contributes or has to be included, say. But it is very much a conjecture. This can only be tested in field theory because you want these free energies to be extensive and scale with the volume. So in simple toy models, like the ones I discuss here, that's not the case because there is no exponential factor to distinguish between the different symbols. There are some ideas that this works. For instance, there's a study, again in phi to the 4, with complex chemical, with non-zero chemical potential in 4 dimensions, where the authors only took this trivial symbol, the symbol that goes through the origin, and found that it was enough indeed to reproduce the results at non-zero mu. Exactly. So there's many. This is very much a conjecture how to do this. Yeah. So interestingly, in this phi to the 4 example, there was a phase transition to a high density phase, and they stuck to the same symbol, and it worked. But indeed, that's very much an open question. Yeah. Now, just to show you, so that is this thing. I'll say in a minute why the residual sign problem looks to be very mild. But just, I want to show you that the case of having more than one symbol is not something unexpectedly. Just again in this very simple example. So again, a simple example. So we're going to use the same model here, same simple integral. So this structure of symbols actually is only when A is positive. So if you consider the same theory, so again 1/2 A plus IB z squared plus over 4 z to the 4. But now I take A to be less than 0. Well, the critical points don't really change. They still have this expression, except that the details, of this complex number change. But let me see where I have the plot. In fact, now all the symbols contribute. So even in these very simple models, this happens. So this is x and y. The critical points are still like this. But now the stable symbol, so the one that goes through the origin, now actually, surprisingly, goes to imaginary infinity, not to real infinity, like this. And then it meets up at infinity with another symbol coming from the other critical point here. And the same happens on this side. So here it meets up with this symbol. So these are the stable ones. And then the unstable ones have to intersect the real axis. And they do that, indeed, in this way. like this. So what has happened here, the original real axis is now completely deformed into going from minus infinity, shooting up to plus imaginary infinity, going down to minus imaginary infinity, and then going to plus real infinity again. So it's like a deformation of the real axis. In this kind of way. All the unstable symbols indeed go through the original manifold. So the intersection numbers for all of these is non-zero, so they all contribute indeed. And then what about the imaginary parts? Well, the imaginary part of the origin is 0, and the imaginary part along the symbol of the two other critical points, so say Z plus, is opposite to the imaginary part of Z minus, so that when you sum up the path integral or the partition function summed over all symbols, it should be a well-defined result, basically, which is what it is. So that's the situation here with more than one symbol. Now, interestingly, you may. So there's two things to say here. Where shall I write them? I want to keep this graph. Two comments. One is, you may wonder what happens in this integral if I change the variable to become plus I infinity or minus I infinity. So I'm changing Z to go to plus or minus I times Y. That looks from my original contour, that's a massive deformation. However, the integral still converges because the integral is dominated by lambda Z to the 4. And if I put this in, I get lambda, plus or minus I y to the 4. So plus or minus cancelled. I squared is minus 1. So this goes as lambda y to the 4, which is still positive. And so my original integral, which has a minus lambda z to the 4 to converge, it still converges in this part of the complex phase space. Yeah. So if I look at this, so in other words, my original path integral, the integration region of the original partition function, can be extended to these cones here, and the path integral will still converge. So the original integral converges after analytic continuation in these hashed areas, so that's fine. Whereas for the unstable symbols go to basically in the complex plane with a 45 degree here, and so there is no convergence in these regions. So the unstable symbols end up in these, the stable ones end up in the regions of convergence. So these are the regions of convergence. So this is interesting. And the second comment is that you may wonder, so I said that there's only one symbol here when A is positive, and there's 3 when A is negative. So this looks like a massive discontinuity when I change A, when A goes through 0. So A is positive. One symbol, A is negative. 3 symbols. So you may wonder about discontinuities. And actually you can work out what happens. Of course, these symbols combine in a certain way. But what's really important is that observables are completely smooth. So observables are not discontinuous when I change this parameter A. And this is something called the Stokes phenomenon. which is exactly when you have different saddle points competing, and if you change an external parameter, the role of this saddle point is flipped around, but the observables are completely continuous in the parameter. As A changes sign. And so this is something called the Stokes phenomenon. So the path of integration is, changes really, really dramatically, but observables are not. So it's like competing saddle points, essentially. And so this is something that also plays a role in perturbation theory. So people study this in something called resurgence to some high order perturbation theory by having instanton contributions. Instantons are also saddle points. So this phenomenon links in with this as well. So it's all quite interesting theoretical mathematical physics, really. So what's the situation here? People have done symbols for lower dimensional field theories. Including fermionic models. It seems to be working okay. Applications to QCD are not yet really existing. I know some of my colleagues have worked on it for a while, but it's not really happening yet. So that's about symbols. Any questions about this? Yeah.
So you said in this case we need contributions from all three simple symbols, but two of them don't seem to be crossing R. How does this fit with the formula?
Yeah. So no, the one that has to cross 0 is the unstable. Maybe I didn't write it correct. Maybe I didn't write it correctly. The unstable symbol has to cross the original manifold. So maybe look back in your notes. Maybe I wrote it wrong, where I wrote about mk, m sub k. It's the crossing of the unstable symbol in the real manifold. Yeah. This intersection number. So in this case here, only this one is crossing 0. So the dashed line crosses 0, so the bold one contributes. And in this case, all the 3 dashed lines cross 0. So the corresponding bold ones continue. Yeah, thanks. Yeah.
So you said that number could be 0, 1, or -1.
Yeah. Yeah, it depends. This -1 depends on the orientation, somehow how you go about it. So I don't remember the exact definition, but in this case it's very easy because you can see that the original real axis is deformed in this way. So that tells you how to integrate, basically. So you break the integral up into 3 contributions from here to here, from here to here, and from here to here. That tells you the sign, the direction of the integral, basically. Yeah. Okay, so we've seen 2 deformations now. One is to go into the complex plane with noise. One is to go to these symbols. But actually, the symbols are kind of the ultimate endpoint, because the imaginary part of the action is constant. But so, is there really a need to find symbols? As some of you commented indeed, finding the symbols is quite hard. But it seems to be that on the real axis, imaginary part of as it's varying rapidly. On the symbol, the imaginary part of the action is constant. So maybe I don't have to go all the way to the symbol. I can just go off the real axis a little bit, and in this way make the sign problem milder. So this is like a middle way. So deform integration contour somewhat. To ameliorate the sign problem. And as long as I don't cross any discontinuity, any pole or any singularity in the complex plane, they should still be fine because the integral should be analytic even on a deformation. And so this is the idea of what's called anti-holomorphic flow. Which basically says it's really hard to find a symbol. Let's just do some little bit of deformation and hope that the sign problem gets milder so we can still tackle it. So in the last 6 minutes or so, I'll give a very sketchy outline of how this works. So for this, actually, I have to start by giving you the equation for the symbol, which I hadn't given you yet. The equation for the symbol is just like a Langevin equation, except there is no noise. So that's why this is this connection with Langevin. So let me remind you that complex Langevin had this equation z dot is minus ds dz plus eta. The symbol has no noise. I don't want to basically have a noisy trajectory. I just want to end up on the symbol. And then it has a bar here, so it's the complex conjugate. And the reason to have a complex conjugate is that in Langevin dynamics, these critical points can be either stable or unstable. Whereas if you take the complex conjugate, it turns out that the critical points are all saddle points. So this somehow ties in with this idea of a saddle point expansion. So if you take this as the definition the symbols, then you get saddle points, and there's an initial condition here. So let me see how to write it. So that as you solve this equation up to infinity, you end up on the critical point. So do we still have some symbols here? So basically this symbol equation, if you solve it, you basically have lines that, that's why it's a stable symbol actually. So if I solve the symbol equation, I will have the critical point by doing this. So actually one way to construct a symbol is to flip the sign, start close to the critical point, that will then map out this symbol. So this is the symbol equation. Now this idea of deforming the real axis a little bit and making the sign problem better is called flow or anti-holomorphic flow. And this uses a tiny modification of this equation, namely just by changing the sign. And here we start on the real axis. So z at t equals 0 is somewhere on the real axis. Now what this equation does for you is exactly what you would guess from what I said in words. If I take this one here, I start on the real axis. This is the critical point. If I solve this equation now, I will end up on the symbol or close to the symbol, but in this kind of way. I can never cross the symbol, but I'm flowing towards the symbol. Like this. So if I would solve this to t to infinity, I would find the symbol, but I don't have to do it. I don't have to go all the way to infinity. I can just stop. And the idea is that the sign problem is worst on the real axis, it's best on the symbol, so anywhere in between is okay. Say that's the idea. Now, how can we say this? How can we make that quantitative? That the sign problem is indeed getting better. So along this flow, how does the action change? Well, that we can compute. So we look at the weight or the action, how it depends on time. Flow time, so t is here what we call the flow time. So s depends on z, so this would be ds dz dt. Well, dz dt is given by the flow equation up there. So this is ds dt ds bar dt. And so, in other words, this is something that's positive definite. Dz dt squared. And so it is positive. So the weight, the action increases on the flow time, and also the change is real. So this one tells us that the real part of the action increases on the flow, whereas the imaginary part of the action remains constant. Now, how does this is the final remark now, how does this improve the sign problem? Well, it improves it in the following way. Suppose that the integral is oscillating in this way, because the imaginary part causes the oscillation and the real part causes this envelope to suppress it. If the real part of the action increases on the flow, it means that this envelope is getting narrower and narrower because it's dropping faster and faster. And the imaginary part is staying constant. So under the flow, what actually happens is that, say this is at, say, 0 flow time. At some later flow time, the real part of the action has increased. I still have oscillations here, but almost nothing out there because this Gaussian envelope is changing. And at even later flow time, I just have 0 here and maybe just 1 or 2 oscillations here left over. So it's kind of an interesting way to solve the sign problem. The imaginary part of the action is constant, but since the real part is increasing, I'm zooming in to the critical point where the imaginary part of the action is then almost constant, because I'm only sampling this very small region here. So that's the idea here. Again, this has been applied to essentially lower dimensional fermionic models mostly. Where it does solve the sign problem in some cases in the way I sketch here. Not really been applied to QCD yet because it's quite complicated to implement this in a gauge theory really. So anyhow, so that was what I wanted to say. So the last lecture is really about approaches that are quite bold. They go far away from anything we know. None of them has really solved the sign problem completely. Complex Langevin is still in probably the most promising one is still in progress. But overall it kind of expands your mind a little bit to look outside of the standard approaches, and there's a lot of interesting kind of field theory and mathematical physics connections here, which may eventually lead to a solution of the sign problem by going into the complex plane really. Okay, thank you.